We are ready to move on to that next topic, and we're roughly on pace for where I wanted us to be this semester. I've mentioned how sometimes these names of the topics, they're roughly matching the corresponding reference material, and this one's called escalation and exfiltration, which is kind of a overly fancy word to describe what we are talking about. Really the big picture of this particular topic, and it will depend, at least in part, based on your interest, and I'll kind of try to gauge the class and see if you're really vibing with this or not, is the assumption with where we are in the lab with what we were talking about last week is you have done those tasks to have gained some sort of access to a system already. If you want to think about it, that you have a shell. You've obtained some shell on the vulnerable system via using some CVE that exploited some weakness, et cetera, et cetera. This stage is really thinking about what next. So what does one do next once you have some access on the system? Now, there's lots of things that one can do next. Specifically, when we're talking about escalation, the idea is you have some access, and now you want more access, which may sound like a similar thing in some sense, but it tends to be a separate set of vulnerabilities and approaches going from no access to some access versus some access to maybe more privileged, more capable access. So when we talk about escalation, it's really privilege escalation. I'm already given or I've already obtained some level of access into the system. Where can I go from there? And exfiltration talks about what kind of things can I then extract from the system that I was not intended to have access to. So we can think of that in some sense as having this sort of lateral or vertical movement within the system. What winds up happening in practice in terms of how this topic has kind of evolved historically, what we wind up talking about with this topic is this is where we really start to look at things like passwords and authentication. The idea being we exploited some sort of vulnerability or we already had some allowed level of access, and one mechanism by which we can do that escalation, we can have that so-called vertical movement, is by looking at how passwords are stored on a system and what potential weaknesses there may be with that given mechanism for storing passwords. Because of that, this topic's kind of interesting because it is going to be, like before, very kind of operating system dependent, just for historical reasons. How Linux stores passwords is different from how Windows stores passwords, and knowing that is actually like relevant knowledge to be able to potentially take advantage of. Where it also gets interesting is, and again, this is where I said I'll kind of measure the class's interest and see how deep we go, is it does have a decent amount of what would otherwise be thought of as like mathematical or cryptographic foundations for this kind of work. Also involves kind of fun programming and the type of code you wouldn't otherwise be looking at if you're just doing more traditional programming assignments in your other courses. And now, having said that, for those of you who are in the cybersecurity minor, cybersecurity major, there is a whole other class, Cybe 3310, whose intended purpose is to cover more of those mathematical foundations and more of those low-level implementation foundations. So we don't actually need to cover any of it if we don't really feel like it, because you'll have that opportunity to take a whole separate class that covers it. When I say mathematical foundations, I think you'll find it interesting, and it's unique in the sense that outside of those studying this particular discipline, it's really involving a branch of mathematics that you otherwise just don't see. So it's not calculus, for example, and maybe that's a good thing for you, maybe that's not a good thing for you. So when I say mathematics, that is true. There is a lot of fairly deep math involved with this. We can still learn a lot by just exploring what other mathematicians have already come up with versus trying to create our own as we go. We'll see how it goes. We'll see how we feel. I've looked at prior versions of this topic, and we've spent several days on it, and other times where there just was very little interest, and either is actually okay. We are at that 1/3 of the way point. We've made it 1/3 of the way through the semester. So congratulations. It's basically what I just talked about here, where we are in terms of our ethical hacking methodology. It's a little bit more vague. We've gained access. That's kind of the prior lab, prior topic. Now, what do we want to do with our current access? How can we perhaps escalate the amount of access, and how can we do things to maybe maintain that access and maybe establish some level of persistence on the machine? Again, though, that itself could be a very wide-ranging topic where the corresponding reference materials tend to focus on is with our current access, that question here, how can we determine what other vulnerabilities there are with regards to how authentication is performed on the system. So again, long story short, the topic is called escalation and exfiltration. It sounds very, very Hollywood. In practice, it's that final question there. We have some access. Perhaps we have some sort of reverse shell, some legitimate kind of scriptable access into the system. What can we do with it? How can we potentially bypass additional authentication to gain additional access or to maintain that level of access here? So this topic is really all about passwords. And I'm going to rely on the class. I'm going to kind of look for eye contact and falling asleep. When we get to 4 people asleep, we'll move on from this topic. But it has to be a legitimate sleep. You can't just have your eyes closed, because maybe you're just deep in thought when we do that. And my bias is I really enjoy this kind of stuff. It's kind of a separate complementary topic to a lot of the other things that we already cover in this class. By kind of necessity, we've gained some level of access. So sort of by definition, or at least it's kind of a tautological argument, we already have, or the assumption is we already have some sort of authentication credentials and have already gained some sort of access to a system. Since, at least by default, we still have passwords as sort of the most common way of doing that authentication, that becomes our next place of looking for how to increase our access or to maintain our access into a system. Now, you may say, and I think it's correct to say, that over the past 2 decades now, there's been a pretty intense focus in considering the fact that when you rely solely on passwords as the main mechanism of performing authentication, there's just lots of weaknesses there. There's the sort of technical or maybe mathematical weaknesses we're going to be talking about today, and there's just a whole bunch of sort of the human weakness associated with that as well. So that is a correct observation and a correct way to think about this, that for systems that don't just solely rely on password-based authentication, you need something else. You need some additional way of gaining access beyond just maybe cracking particular passwords. But there's all sorts of ways that one could also consider that as well. We'll talk more as the semester goes on about social engineering attacks at a pretty high level, and other ways in which some sort of non-technical approaches can be used to gain access to password. Today, we focus on passwords, basically cracking passwords. What does that actually mean in practice? You're doing it in the lab, but you're just running a command. What is actually happening when you're doing that command is what we're going to really understand today. And then later we'll talk about more common two-factor, multi-factor authentication system, things like biometrics as well, with an understanding of what that really means in practice. I listed this here that we like to think that as those who are studying cybersecurity, we ourselves are not going to be those who have been hacked, have been pwned. And I bring that up as an example. I was going to put in my own account here, but I decided against it. But if anyone's willing to volunteer an email address, go for it.
I know I've been pwned. Okay. TROYTOMSON114@gmail.com.
It's very brave of you. Okay. Because I didn't want to do it for my own account. So everyone should go, when they have a moment, check your Gmail or something like that and to see. And by the way, thank you, Troy, I appreciate this. Before I click this button here, you can be on this having done absolutely nothing wrong yourself, right? We are pretty much required to interface with lots of third-party services, and everything requires it now. And we can look at these various pwnages or data breach, let's call it that, and it's really the companies or organizations' fault to what extent? Just not too bad. That's not too bad at all. So you have an account on archive.org, and they suffered a data breach that exposed 31 million records. Oh, that's pretty safe. Anybody else willing to volunteer? Sure.
Isaiah, ISAI,
I didn't catch the left. 1688. Well, we're going to find out. How is that possible? All right, fine. Since I let you guys volunteer, and everyone should check this if they have. Oh, go ahead, sure. BCY? BCY BH. Cyber. Ah, okay. Cipher makes more sense. Okay. I'm impressed. It could be the age of your accounts. All right, we'll do it. We'll do it. Ah, it's not good. That's not good. Okay. During 2025, the threat intelligence firm, blah, 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 aggregated 2 billion unique email addresses. Well, 2 billion. Okay, so that should be most of y'all. Internet Archive gets us all. I have no idea what Nas.api is. This is kind of a risky click if we're being honest here. Not Duolingo. That's why I stopped learning French. Ooh, Twitter. Don't know it. Zynga. That's a video game company, right? Or they were. 2023. It's interesting. I mean, there could be a lot going on there in terms of how one signed up, whether it was through kind of third-party Google authentication or an account using that email address as a separate account on their servers there. I'm apparently the most pwned person in this class. Well, my account's probably much, much older, so I've had to go to, I'm not going to click any more of that. Anyone else want to volunteer who hasn't checked it yet? I'll put it in for you. Sure, go ahead. GMI? BI? Okay. You guys have too long of, maybe it's just your, 1, 2, 3. Your accounts are just too long. Maybe that's why they're not in the data breaches. They don't have enough. Uh-oh. Boat. The Indian audio and wearables brand. Sorry to hear it. So, okay. So what the point was there, I'm still the most, obviously, pwned person here. That's just in indicating that, and this website is just an attempt to kind of collect various other well-known data breaches. Some of those are just account name breaches, but others are account and the exact kind of information we're going to be talking about here today. So there is, I would say, some risk that if your account shows up in that website or other data breach websites, that is a sign that potentially you're especially vulnerable to types of password cracking here. Let me know offline, post on Discord if anyone has a more pwned account than mine, which had 12 or 15, whatever it was there. I guess the number's only going to go up. It never goes down. I was trying to tell my same kids we were talking about before class that there was a time when a Gmail address was a very difficult thing to get. You had to know someone who had one. It was limited invite, and it was considered like a valuable thing. That's not the case anymore. So the mathematical background, and if you want to think of it as sort of like an applied cryptography background, or even just sort of a very specific type of programming background, has to do with this concept called hash functions. I want to start with just a show of hands, and it's okay just to be honest here. Who here is familiar with the term hash functions? Did it come up in 2300, at least to some extent? Maybe you know all this, that's great. Let's review it again, and just from my perspective, maybe you will still learn a thing here. A hash function. Any function that can map an arbitrary sized input to a fixed length output. And I think if we want to be a little bit more precise with that definition, a hash function, and there's other terms you'll hear like a digest function, is anything that can take a lot of data and generate a smaller amount of data from it. It's like digestion, so it's like digesting food, or hash is like scrambling together things together. I say arbitrary sized input, but it could be arbitrary within some bounds. And almost always, if it's a hash or a digest function, it's a fixed length output. So you think of it like a function, like a mathematical function, or just a programming language function that takes some input of m bits, capital M bits, where m is variable, and generates some output of capital H bits, where that H is going to be fixed. Like 32, 64, 128 bits is H. And the assumption that the whole point of using this kind of function is that H is going to be much less than M. So I'm taking in a decent amount of data. We'll talk about its use in passwords and authentication, but let's say I'm taking 1 megabyte of data, and from that I'm going to generate a 32-bit value here. And that's the flow of this, that you take some input data, there's your many bits M here, you then apply some function. You can call the function H, but we also refer to the output as being H here, and we generate that fixed output data here of H bits. Some of this is going to be a little hand-wavy when we talk about whether something is a good hash function or not. There are various mathematical properties of these functions that, depending on the usage scenario for them, we care more or less about. Sometimes we just need to get something done relatively quickly, and performance, the actual runtime performance or latency of it is what we care about the most. Other times we care a lot about sort of either the pre-image or other collision properties of the hash function. But in general, the idea behind this for a quote-unquote good hash function is that any small changes in the input M bits here, even think of it as just flipping 1 bit. So I have 1 million bits, and I flip one of those bits. The concept behind it is that even just doing that, making a very small perturbation of the input, should lead to a relatively large and certainly non-obvious change in the output. It seems a little magical. Let's just walk through what that looks like in code and how that happens in practice. Here's a very well-known hash function. One thing you'll find when you look at these, certainly for the non-cryptographic hash functions that are still very heavily in use, is they tend to just be one clever person who just came up with a few ideas, and they were found to be good enough hash functions. And so they have names like Jenkins hash function. There's nothing wrong with Jenkins hash. It is used in all sorts of places still. As far as I can tell, roughly from 1997, and sort of published in the computing professional magazines of that era. One thing you'll note is this is C code here, and it looks maybe a little different than the C code you would otherwise normally be writing for some of your classes. But we'll look at a couple of other examples here. They all tend to look like this. They all tend to, while there's differences in their implementation and some of the theory behind them, the code for them all tends to kind of look like this. So you'll get more used to reading that kind of code here. This is just C code trying to be a little clever. So Jenkins, 1 at a time hash, takes as input a pointer to the block of data that we want to hash. That is our M here, where it's an 8-bit chunk, so it's an unsigned 8-bit value here, and then the number of those chunks we're wanting to process here, and then it's going to return a 32-bit value. So what is Jenkins hash function, or this version of it? It is a 32-bit hash function, or capital H is 32 bits long, and it takes, I think, a pretty arbitrary number of 8-bit input values and hashes them all together. Well, what does it actually do? It's going to kind of look like magic or nonsense, depending on your perspective here. Goes byte by byte. So there's our while loop here. Hash plus equal key of I plus plus. Take the next value of our input M, the next 8 bits of it, add it to the value of hash. Literally addition operation here. Take that value of hash. Does anyone know what this operation does here on this line? Left shift by 10. Why 10? Why not 11? Why not 7? There's probably a version that does those. You try a bunch of things, you see what kind of resulting property it has on arbitrary data. Shift to the left by 10, add that. Now take that value. What does this operation do? That next line here. This is C code you don't write a lot, unless you're doing crypto or hash functions. Right shift by 6, and what else does it do with it? It's an operator you probably don't use unless it's on a programming assignment. XOR, does an XOR, does a bitwise XOR of those values. Who said digital logic wasn't useful for cybersecurity engineers? Do a bitwise XOR of that value that's shifted to the right, and do that just over and over and over again. And then at the very end, once we've gone through the entire thing, do one more arbitrary thing, I don't know, just for the heck of it. So this is an actual known hash function. It's not considered a bad one. It's old, but in terms of non-cryptographic hash functions, it's perfectly considered adequate. They all tend to look like that.
So is this Jenkins hash function, are all those numbers like exactly like hard-coded, or is this just a format that's
hard-coded. So when you run this hash function, and we'll look at another example just to show like what does it look like in 2026 here. Yes, those are hard-coded values. It will shift it by 10 and then to the right by 6. It has to be reproducible. That's part of it. It has to always give you the same result for the same input. That's another property of our hash function. But if we go back to the good idea, the hope is that you make a small change in the input, even just flipping one bit, and will result in a large, non-obvious change in the output. Well, why does this accomplish this? It's a little hard to say, other than we're definitely trying to mix up all the bits a little bit here. You shift to the left by 10, and then you XOR shifting to the right by 6, and then you add in this value, which, addition, numeric addition here, integer addition here, also does some manipulation of the resulting bits. The end result, and I did run this code, these are not fake values, and this was more effort than it should have been, is if the input was Joseph Zambrino, you run that text string, if assuming that's ASCII text, through Jenkins hash function, you get this result back out. Whereas if we do a very common misspelling of my name, Joseph Zambrino, you get what looks to be a pretty reasonably different version of the same hash function output, or other extremely common output, Joseph Zambrano, and you get also a completely different thing. So there, we didn't flip one bit, we flipped one ASCII character. I guess we could probably figure out how many bits that is, but it's just a couple bits that we flipped here to go from E to I to A. And the result, even though that's all we're doing to it, a bunch of additions, a couple XORs, some shifting, there's tests we can run for how different it is, how random does it appear. At least to the human eye, it's reasonably random. As part of that, small change in the input leads to reasonable large change in the output. You have this other kind of the flip side of using a hash function. We start with a lot of data. Well, it's not that much, but here of 12, 14, 16 bytes of data, whatever that is there. We generate 4 bytes of output for this hash function. We are always going to have, by sort of mathematical certitude, by design, we're always going to have what's referred to as collisions in our hash function. It is fundamentally unavoidable. When we go from a lot of potential inputs, if we want to be literal, if we go from 2 to the capital M possible unique inputs, right? We have capital M bits of input, that's 2 to the M different inputs we could have, to only 2 to the H possible outputs, right? And I tried to visualize that a little bit here, right? We have a 32-bit output, there's only this many possible outputs. It's a decent number, right? Whatever 2 to the 32 is, 4 million outputs, right? $4 million, 4 billion, which one is it? 2 to the 32 is 4 billion, thank you. Okay, it didn't sound right when I said that, thank you. That's a lot, but that's nowhere near as many as there are potential inputs for any value of M, I guess, greater than 32, which it would be here, right? For we have a number of bytes here. So you're always going to have collisions. It's just unavoidable, right? When you only have this many outputs and this many inputs, there's going to be many, many, many different inputs that have the same exact output of our hash function. That's what's referred to as a collision. And I did waste some time just trying enough possibilities to get to a value that does hash to the same exact input value here. We're going to talk about what that means for passwords, and it's not quite as simple as saying that means, that this could be used for that if that was the password, but it roughly indicates or implies the same mathematical certitude here, that we have seemingly arbitrary number of potential inputs to our hash function, a large 4 billion, but not infinitely large potential space of our outputs. There's always going to be a certitude that there's going to be collisions, that 2 totally different inputs, and it's going to be many, many, we can do the math, different inputs will lead to the same exact hash value here. The question is, or the challenge is, how easy is it for me to generate that arbitrary string, and how much effort does it require? How much permutation, how much iteration does it require? Just ran a script that just kept trying. Just let it go. I have the code here. It's in, I think it's going to mess up the recording if I show it to you. I don't remember because I did it a couple years ago. It didn't take that long. We talk about 4 billion as being a lot, a lot of possible. It's not a lot anymore. 4 trillion is a lot now. 4 billion is not a lot. So going through that, it's really silly code of just keep trying. I don't remember if I tried random strings. It must have been a random string. There's no way that's an incremented string here. So just try random string in a loop, get the hash, see if it matches. Try again, try again, try again. And you only have to, you're guaranteed to get a result. Well, what's the birthday paradox here, right? This is for a specific one. Well, you're guaranteed to get a result if you run it 4 billion times. It's not a lot. In this day and age, 4 billion is, it's decent, but it's not considered a lot of times, right? 2 to the 32 iterations is something that you can write a piece of code that has that big of a for loop. 2 to the 64 is still very much pushing it. 2 to the 128 is, infeasible, right? So you just kind of do them all. Hashing is not the same as encryption, but they're very interrelated concepts. It's a lot of the same people, and a lot of the code tends to look very similar. Is this a hash function or a crypto function? It's hard to tell just by looking at a few isolated lines of code. It depends on the intent and other things that are happening here. And again, not all hash functions are known as sort of cryptographic hash functions. There's just this more generalized grouping of hash functions that are used for you can still think of them as security applications, but really not entirely security applications. So, for example, cyclic redundancy checks, like CRC checks, checksums, or another way to say that, CRC is a type of hash function that determines whether your credit card number is a valid credit card number or not when you enter it in. So a website could determine if the credit card, whether or not it's a valid American Express or Visa, whether it corresponds to your account or not, that's a separate check. But it can tell if the numbers themselves are valid by running a relatively straightforward CRC to determine this last digit has to be a 3 because it's basically running a hash function on the previous, whatever it is, 15 digits of your credit card number. Or you have a barcode and the last value of your barcode is actually a hash output that lets the scanning software know that, yes, it actually scanned it properly. Otherwise, that last number would not be correct here, or statistically unlikely to be correct here. Those are also all hash functions, whether you think of that as security applications or not, just computing checksums. I'm going to host this very large file, and you're going to be spending, an hour downloading it. I want to also provide alongside it some sort of hash, some checksum value that will let you know if you actually downloaded it all correctly. And you download the whole file. Your downloader actually then runs, once it's done, the same kind of hash function on it, and it just compares those two results. And that gives you some confidence, and we'll talk about the collisions and those implications as well. Gives you some confidence that, yes, I either entered in the credit card correctly, or I scanned the barcode correctly, or I downloaded that entire file correctly. We'll talk about why it's not necessarily a guarantee, but it provides some confidence that that is the case. Another common use of hash functions is for those programming languages like Python or PHP or higher level languages that provide dictionary data structures that allow you to relatively quickly look up if a value exists in your data structure or not. I have a complex data type, and I want to know if this collection of those complex data types, if this particular value exists in it or not. And I want to be able to do that without doing a linear search through the entire data type. That's why we have these so-called dictionary data types, where I want to look up a word in a dictionary. I don't do so by starting on the first page and then going to the next page and the next page. You can. It's very inefficient. I know it starts with the letter D. I go to the letter D. I know the next letter is A, or let's see, letter Q or something. I go to DQ in the dictionary. Let's say D-O, and then I go to G for D-O-G. I can't think of any words that start with D-Q here. That's a dictionary data structure, and the mechanism by which those words, those data types work is also by using hash functions. So we can take a look at Python's implementation of its own dictionary data structure here. Now, I like to quiz people, as you've noticed as the semester goes on, and I ask, what programming language is this written in? This is written in C. So I said this is Python's dictionary data structure, and it's written in C. Well, the Python infrastructure is kind of interesting. Historically, conventionally, Python itself was written in C. There are now sort of native Python versions where it's kind of bootstrapped Python upon Python. But for the most part, if you are using this wonderful programming language and all the frameworks that are provided on top of it, the fundamental engine that's running that all is still being implemented in C. So they provide this data structure, and because it's part of the C Python implementation of Python, they would use a hash function to provide not exactly random access to it, but a very efficient lookup into a data structure. I want to know if dog is in my dictionary or not. And one way one can do it, and let me go back to this example just to illustrate what I'm talking about. I'm referring to text here, but it could be any arbitrary data type here. I want to know if Joseph Zambrino is in my data structure spelled correctly or not. One mechanism by which I can create that data structure is by a hash function for which I'm not actually checking, at least not at first, whether that input message is in my data structure or not. I'm checking whether the hash value is in my data structure or not. So when I want to look up whether something exists or not in my dictionary, I perform the hash function again and check. Is it there or not? With the caveat, when you're doing that via a hash function, you have to double check your work. I want to see if that string exists in my data structure or not. So if I'm using Jenkins hash, I'm actually going to check if this is valid or not. But I have to double check my work because mathematically it's possible that in fact it was something completely arbitrary that was in my dictionary instead. So you do both. You apply the hash function to confirm, is this a possibility that it exists or not? You get the true negative right away. Oh yeah, this doesn't exist. We know for certain it's not in there. If we think it might be in there, we actually have to go in and do the actual comparison and do the actual check. It turns out that's a much more efficient way than just doing sort of a search linear or otherwise through your data structure. We apply these hash functions to determine, does this arbitrary thing exist or not here? So you have these somewhat arbitrary data types that you can create in your own code that you write in Python, right? And as part of it, you can add it to a dictionary type. So it can have numeric types, it can have non-numeric types, it can have strings, plus any sort of combination of that at the end of the day. And what this code does is it performs a hash upon all of that and stores that hash value in your dictionary. You can actually print out and see the actual value that's stored if you want to know the value that's in the hash output. It's not really useful, but under the hood, that's what's happening. It calculates those values again, checks to see, is it in the dictionary or not, or does it need to be added to the dictionary here? In this case, for numeric, you just read the comments here. For numeric types, the hash of a number x is based on the reduction of x modulo the prime p, which is just an arbitrary value provided here. And the goal of that is, the hope is that for numeric types at least, if the hash of x is equal to the hash of y, then we believe that x is then equal to y. That's not possible for arbitrary things, but for numeric types that could be possible. Then with some rules of what it does if the value is negative. If it's negative, actually take negative the hash of the negative of the additive inverse of that value. Check for certain edge cases, like if the value is infinity or negative infinity, and return some value for that as well. And the actual code for it looks kind of like magic, but what does it also look like here? Not so different than Jenkins hash function here. For my input value, while it's still not 0, take the value, shift left by 28, do a logical AND with that kind of arbitrary value, multiply by, I believe, 2 to the 28, then just kind of continue that loop over and over and over again until you get a hashed back result. Not so different than our Jenkins hash function. That is one option for how it does the hashing. It also hashes pointers. It hashes buffers. I'm trying to think if I have an example here. More shifting to the left and doing addition of that value as it increments through the pointer. Very similar to the Jenkins hash function here, with some XORs at the very end. Again, just as your question is before, those are all just hard-coded things that are part of the implementation here. I'm trying to think if there's anything even more crazy in this implementation here. There's different choices of hash function that the builder of CPython can determine which one it's actually going to use. For now, just kind of squinting at it is sort of the level of understanding we pretty much need to have. That code is very similar to the Jenkins hash function I had there on the slide. XOR, that's dereferencing a pointer, shifting, continue to do so in a loop here, and then just do some final XORing at the very end to get that kind of arbitrary value back out. See if there's any other examples here. This is SIP hash. This is a relatively recent hash function, just last 3 or 4 years here. This one was created to be more sort of amenable to hardware implementation for reasons that aren't really obvious when you look at the code for it, because it does look very similar to even just the Jenkins hash function. The other thing you will see in these implementation are somewhat seemingly magic values here, and that's effectively what's happening here. Values that have enough sort of diffusive properties such that when we start with our input buffer and we start by just XORing these values, in this case it could be key values that we specify with these arbitrary hex strings, just arbitrary 64-bit values. You start with some just effectively what appears to be randomization of the result, and then the end result, additions, multiplications, shifts, and XORs. The end result is still just a fixed length value that we have here. I think that's enough examples. But that is, and that's not a code base that's older from 1997. That is a code base from today. That's how hash functions are implemented in practice. They just tend to be chosen by empirical testing. Does this particular somewhat arbitrary kind of mathematical approach get reasonably good results in terms of the performance? How long does it take to execute? How well does it kind of hash things together? How well does it chop things up? And then that one gets used, and it's used until it doesn't have, it's seen to not have sufficiently good properties here. But they don't make those guarantees, and it's ultimately, if it's in this bucket of non-cryptographic hash functions, or if you just want to refer to as general hash functions, it doesn't try to make that guarantee about how difficult it is to do that, to create that collision, to find that collision. And we'll talk about why that does become important when we refer to, and you'll see the term a hash function being broken, or deprecated may be another term you would see used, that, oh, you shouldn't be using this particular hash function anymore. It really depends on the intended purpose. And it tends to have to do with that final question of how hard is it to generate identical hashes for different inputs. We can refer to the example of using a hash function for providing guarantees of the downloading of large files. Here's this large file that you would like to be able to download. Here's a hash value I provide alongside the file. A lot of files do that. You just may not realize that's also being checked alongside. In some sense, the original intention of those kind of checksums was just to guarantee that, like, my download was actually correct. That, like, nothing got dropped along the way. My software was buggy and it didn't download everything. In practice, over time, that started to become used as something of a security guarantee that the file hadn't been tampered with either. That if the checksums are constant, they didn't change, that it provides some guarantee that the files themselves are constant and hadn't changed. Once we switch the purpose of that hash function from just kind of providing a guarantee that your download wasn't broken to now providing more of a security guarantee of the integrity of the file itself, then that question of how hard is it to generate identical hashes for different inputs now becomes very important. And now the choice of our hash function can't just be something that works pretty well, like our Jenkins hash function. Bob Jenkins is a real person. He's still alive. I hope he's not watching this lecture. His functions are great. Because that now becomes a threat. If someone is able to modify the file, assuming for some malicious intent, and not just modify the file and do so in such a way in which we get the collision here. We get the same hash function. Now we do have a data integrity issue, a real data integrity issue. Now we maybe have to be a little bit more careful as to the nature of the hash function that we are choosing here. That's why you're going to see, as we talk about, again, a little bit of alphabet soup of the different types of hash functions. It's why you're going to see these two buckets of functions and some crossover between one bucket and the other. Again, the code's all going to look very, very similar. XORs, shifts, adds, multiplications, that's all they do. There is no magic extra function we can do here at the end of the day. And there's a fairly mature, branch of mathematics that talks about, the properties of doing those type of operations. But we have this bucket of hash functions that are just there to make sure that something didn't get dropped along the way, or that we can look up something in a data structure. And then we have that other bucket, the sort of cryptographic hash functions that are intended to provide certain guarantees that if you modify the input, we have some guarantees. You can't easily do that without also changing the output hash. And the corollary of that is equally important, that if two inputs have the same digest, it should be extremely likely, however we choose to define that mathematically, that they are identical. And then finally, and this goes into the cryptographic nature of it, the given output should appear to be essentially random. And when I say that there's these two buckets, there's the generalized hash functions and there's the cryptographic hash functions, and we sometimes move one function from one bucket to the other, is that to the extent that one can make, it's certainly this first guarantee, but these three guarantees changes depending on the evolution of the branch of mathematics that looks to attempt to sort of break these things, and also changes in terms of what is computationally feasible today versus what was computationally feasible a generation ago. And so that's why you'll see this evolution of hash functions, although when we look at the implementations of them or just the pseudocode for them, they're all going to look really, really similar. It's because of a recognition and an evolution of which ones are appropriate for different tasks, whether generalized tasks, just go for something quick that gets the job done, or for these cryptographic tasks that are going to be used, for example, to store password information. We need to have those properties for this to be a useful hash function for that purpose. Let's leave things here for today, and we'll pick up and start talking about passwords and how these are used for password purposes on Thursday. Thanks.